Thanks very much for inviting me to come to here to share the research work we carry out at the Hong Kong Polytechnic Universities. The title of my presentation is Investigation into Structural Behavior of High-Strength 690 Steel and their welded sections. I think high-strength steel have a lot of promises. I think the problem is how to reuse it as engineers to build heavily loaded structures. One of the questions I was always asked by engineers is about the welding. Rather, we are able to have effective weldings. Just some slides for the center. Chinese National Engine Research Center for Steel Constructions, Hong Kong branch. We work closely with the Development Bureau, CITAC, and many other industrial organizations in China. In simple terms, we try to promote Hong Kong as an international design center for infrastructures, while in China, it is the International Construction Center for Infrastructures. We are looking into high-strength steel. Normal grade steel, 235, 275, 355. We are trying to look at a double of all these strengths, 690, 960. And we have been working on this project for about 5 or 6 years. We will actually offer something about 1,400, and they are steel plates. In China, we are actually the biggest steel production country in the world, producing over 50% of the whole world production. It's a large amount of materials, and we are trying to explore using high-quality steel material from China for construction in Hong Kong, as well as exports. We believe in high-rise buildings. We believe in the need to build more houses, residential buildings in Hong Kong, which is actually very relevant nowadays. One of the important things we need to sort it out is there is always a understanding, say that when you have a higher strength steel, there's a reduced ductility. And this test basically tries to demonstrate to you high strength steel is able to move or deform rigorously. The number we have measured here is 10% strength. And you can see that under different cyclic loading, the steel coupon is able to deform satisfactorily. I think the real question is that if you want to use it in building structure, how much we need? Well, we're going to show you a number of experiments we have carried out to demonstrate its applications. I mean, the whole idea is trying to convince all of you, maybe some of you, okay, to use high-strength steel, okay, if we are able to demonstrate technically that we are able to use it as a structural engineers. We carry out a number of tests using 3 steel plates, 16, 10, 16 mm thick into different cross-section, C1, C2, C3, C4. We have done that 2 or 3 years ago, a stocky column under compression as well as stocky column under combined compression and bending. The test is simple if you got the right equipment. We carry out axial compression force, okay? You can see the deformed shape as being shown over here. We can show you the measured structural characteristics, axial load shortening curve. The maximum value we got here is about 8,277 kilonewton. We need a big machine to do that. And comparing with the simple design rules, yield strength times the area, we're able to show that all the steel specimens is able to reach the design strength by a few percent more, 1.07, 1.03, 1.01. We repeat the test once again using long columns. So it's once again the same cross sections, C1, C2, C3, C4. Member length is about 2 or 3 meters. As you can see here, 2 meter, 2.8 meter, including this is the physical length, including the pin condition. Effective length is about 3 meter. Well, it's working very good. You can see the physical test we've carried out, measurement load diffusion curves, as well as the numerical modeling of our slender column. Well, in simple terms, high-strength steel columns behave exactly or very similar to what we expect on normal grade steel. Column, because of its slenderness, under compression, it buckles. No, nothing new. But in a sense, we are able to apply the existing design method for cross-section resistance, member buckling resistance to design high-strength steel. So this is something we are able to hope that helps you to adopt such a steel materials. We have actually carried out a total of 7 of them. We call this one confirmatory test for use of current design rules. Putting into the Eurocode systems, what we can say that is with different slenderness, looking at this axis, all this test specimen is able to perform better than the current design rule, which is curve C. So we got the test data here. We got the stocky column here. So it works very well. Now, in order to transform the test data into a codified data, we need to provide numerical simulations, allowing for the geometrical imperfection as well as the residual stresses. We have done all this, and at the moment, we have actually present our results to the Eurocode Technical Committee in Europe. Okay, the technical executive editor is actually in UK. Okay, so we are able to demonstrate, provided with all this test data as well as the numerical data, we are able to improve the curve C to curve B, and probably into curve A. Okay. If we have control all these structures in a better way. Well, similarly, we've carried out all this slender column under combined compression and bending. So it's the same setup, but the axial load is being applied offset to the column with an eccentricity 100 mm. So once again, it's pin-pin connection for slender column under combined compression and bending. And we have done all these tests once again, and they deform as expected with a similar steel material member. Current design rule in Eurocode, once again, we are able to adopt the curve A0, comparing with the test results. All these columns is able to perform very well according to the check values over here. So it seems member high-strength steel is okay. No, nothing really new. Okay, all these are being confirmed. Now the questions come to the welding. So we have actually talked about different welding, heat effect, microstructures, all these metallurgy systems. So this diagram basically shows you that with the welding process, the fusion line is here. You have a big increase in the temperatures, and it cool down accordingly to this distance. So the metallurgy really is trying to say that the high-strength steel gain the strength because of heat treatment. And they've done that in the steel mill during their crunching and tempering process. The problem of welding is that they try to restart the whole process again with little control. That's the problem. Okay, that's the problem. By providing a large heat input inside the structures, they are going to have grain growth. In simple terms, is they have sufficient time for them to grow, and that change their crystallizer form, and that cause strength reduction. Now, that's all the theory. What we have done is that in order to carry out all these tests, we work on the robotic weldings in order to control the welding quality. Well, at least we are able to get coupons, test specimens with consistent quality. Now, whatever quality, it doesn't matter, they are consistent, repeatable, so that we can improve the situation on. So this is a typical setup we have at the Polytechnic University, showing the different camera taking through of the welding process. This is a regular camera, and we have an infrared camera as well as a welding camera. So we are going to show you what those images collected. So you are looking at the normal welding process. You can't see much. It's too bright. You can't see much, really. We have this infrared camera showing the temperature change. The red spot is basically the arc. And think about what you see here. I think we have just stopped it. So basically, you are looking at the weld pool. By shielding off all the bright light, we're able to see the melted welding materials at a temperature about 1,300 or 350. By looking at the weld pool, we are able to see the quality of the welding. We are trying to improve the welding quality, now not by looking at its defects after welding. We are trying to solve the problem, if there's one, right at the spot. So there is some change in their thinking in order to do that. So we work it through, showing you different temperature ranges. I think I need to run a bit quickly. This is the images taken from other people's, showing the quality of the welding by looking at the welding process. And surely you can see some of the welding is not good enough. Some of the parameters went wrong. Okay, you have a lack of the shielding gas. We have carried out a number of testing to work out the welding process. What's the effect of the welding onto steel metal, especially high-strength steel metal? So we have done a butt joint. We machine out coupons. All these welded sections are being carried out at controlled heat energy input. So different number of passes, 1, 2, 3, 4, with different amount of energy input. Well, it's a long story, but what we can say here is, comparing to the weld metal, the high-strength steel metal is the one in black. So with a high energy input, 5.0, that is a significant reduction compared to the parent metal. But this is an interesting line. By controlling the heat input during welding, the light blue line show they follow closely to what we have for the base metal. So the control is actually very important in order to achieve the same microstructures. This is the results in tension. We have also carried out full-scale tests, columns in compression. You can see some of the heat affected zones after etching of the test specimens. Now, in order to look into the effect more, we go quite far. We have done quite a lot of work at that area. It's the heat affected zone. I think the idea is to simulate the welding process using what we call a physical welding simulation machine. We have actually fly to Beijing, okay, to work with some steel mill to use the equipment to do the test. So this is the equipment. By providing through the electricity, if it's running. You are able to see the coupon grow quickly according to the time temperature curve, and that is what happened when you try to weld the steel plate. And after doing that, we've carried out coupon test, tensile test on this. What we try to do is that by heating it up at different temperature according to the welding temperature graph. Thank you. We are able to simulate the exact microstructures as being shown over here. So you can see, if you are interested in microstructures, you like all these FEM images, martensite. They're all martensite, very good. I think the problem is this one, the tempered martensite. So we are able to look at the change in the microstructures, and we're able to see the strength reduction. So this graph here basically corresponds to here. This one, the other one, okay? So this is the problem where they correlate to this one. So you can see there is a mechanical evidence of the microstructures. This is the case for 1-point rod, so kilojoule per mm, so you can see that it's not a big problem, okay? The problem comes when you're using 2-point rod, and you can probably see a slight reduction in their strength. 5-point rod, you have a problem. We have seen that. Okay, so this is what we do. I think in terms of the time, I will probably show quickly to the last one. Application of all this strength. I don't know, after showing all this experimental work we did at PolyU, we hope that you can see all these are evidenced. In Hong Kong, there would be a steel bridge going to be built in Tseung Kwan O. Well, I think all of you know where is Tseung Kwan O. So this is the Causeway link, linking up from this point to this point, about 1.8 kilometers. And in between this part, you have the steel bridges. Well, it's architectural images. It's not there, okay? Not yet, okay? It will come in 2022. So this is the images, okay? You see all this is being operated by the Civil Engineering Development Department. So this is the design. From here to here, okay? It is a steel deck with steel bridges. The arc, they are fabricated boxes, 3 meter by 3 meter, with a plate thickness varying from 50 to 60 mm. They are all made of 690 steel, okay? And they have expressions as the eternity arch, and I think I give this one to Chris. If you are looking at this side of the edges, you can see an infinity. The 690 steel, 4,400 tons. The whole bridge from this portion to this portion weighs about 12,000 tons. They will be fabricated in Shanghai. The whole bridge would pre-assembled and pulled down to Hong Kong and lift up onto the piers. Very exciting project. I look forward to see this one. And that's all I want to say. Thank you for your attention.